Today we're going to be talking about electron energy levels. Now this is actually a topic you guys are pretty familiar with. You did a lot of work with it in chemistry. We're just going to be taking kind of a more numerical approach to it and seeing how these electrons, as they go from excited to ground state to other excited states, the actual energies involved as they move up and down through these energy levels. So, before we begin with that, we're going to talk a little bit about just the basics behind the Bohr model for the hydrogen atom. Now, when Bohr designed his model, he was looking at the photons created from energy transitions, or the photons created from energetic gases. And he used that to build his model of the atom. Now, when he made his model, he actually knew that this was not the physically correct model. However, he knew it was a good approximation and that it would move science forward. So he put it out there, and then of course shortly after, the wave mechanical model became the correct model of the atom. But the Bohr model still is very useful in how it allows us to predict exactly what's going on inside of an atom. So in under his idea, he has the electrons orbiting around the nucleus in set paths, which are referred to as orbitals. Each of these orbitals corresponds to exact energy, depending on what atom it is. It could be very different energies for each different atom. And then we have a couple of notations we have here. You can see we have these n values given on this side over here. The n equals 1 is correspond to the ground state, or the lowest energy level. This, by the way, is representing a hydrogen atom. And any level, any ring that's higher than that is referred to as an excited state, where it has more energy than it does where it would normally be at. So how does a electron get to an excited state? Well, the way that we're going to be looking at today is the absorption of a photon. So essentially, when a photon of the correct energy, that's the key, and I'll talk about why in a second, hits a electron, it will move up to a corresponding energy state, and which is referred to again as the excited state. Now, the reason why it needs an exact energy, exactly the correct energy, is because these electrons can only go to these set levels. They can't go in between the levels. And that's a very important finding for quantum mechanics, the whole idea that there's only a set amount of something, which is referred to as a quantized amount of something, which is where the term quantum mechanics comes from. So these electrons can only go and only gain the energy that sets them to an appropriate level. So the photons that hit them, they can't just be any energy. They have to correspond to one of these energy levels. Now, when an electron is in an excited state, it will eventually move back down to the ground state spontaneously, which means nothing really has to tell it to do that. It will automatically do that. The classic saying, what goes up must come back down. So as these electrons are excited, they're eventually going to move back down to the ground state. So when it does that, when it spontaneously drops to these states, it will release a photon of light of the corresponding energy. And this is going to be the energy of that photon, and the color of that photon, the frequency of that photon, is based off of the formula we talked about in the last one, which is the E is equal to H times F. And so that can tell you what frequency the photon will be when it releases. So in this case, we have a blue photon created when it's moving from this higher energy level to the n equals 2 state. Now, do note that that doesn't always drop immediately down from the highest level all the way down to the lowest level, to the ground state. Sometimes it can take steps in between, which is showcased here as it jumps from the, what is that, 1, 2, 3, 4, the n equals 5 down to the n equals 2 state, and then eventually it would drop down from the n equals 2 state back down to the n equals 1 state. So it doesn't always go from the top down to the bottom. Sometimes it has steps in between, which is why you can get a wide variety of photons created from an excited hydrogen. So again, these frequencies of photon is based off the energy. Now, what is the formula to determine the energy? Well, it's the energy that's initially at minus the energy that's at its final point. So what energy was the electron at when it was in the higher state versus what energy was it at in the lower state? And this formula works both ways. It works for the emission of photons. It also works for the absorption of photons. You're just trying to figure out how much energy did it gain or lose as it went up or down. Was a photon absorbed? Was a photon emitted? So what are these energies? Well, we get this right off of the energy level diagrams that we can find in the reference table. So on this side, on the right side of the screen here, we can see we have different energy levels with different corresponding, let me just move my camera over here, oops, down over here. We have our different corresponding energies on this side over here that relate to the different levels. So at the lowest level, at the ground state, you can see it has a minus 13.6. Now, note the unit of the energy here is in electron volts. So that's important to note. And then we have the different levels. You can see the n equals infinity is at 0. We'll talk about what that means in just a second. But that's the basic idea. So you can figure out the energy of any of these electrons just by looking at this diagram. You can see that they start off very spaced apart, but then the energy levels get closer and closer to each other. So once you're inside this kind of patch of energies over here, you want to look very carefully, make sure you grab the right proper energy for that. Okay, so in a hydrogen atom, if we have an energy level drop from 6 down to 2, what is the energy level of that photon emitted? Okay, so in order to do this, we're going to have to find the energy that it was. So the n equals 6 looks like it is that negative 0.38, and then minus our final energy level, which is negative 0.340. So if we do this math out to find what that energy was, we get a total energy of 3.02 electron volts. So that's my total energy. Now, the second part of this question on this page, we can see we have what type of electromagnetic radiation is this? This is actually a multi-step problem, and I'm going to walk you guys through this at the very end of this video. But just know that we're going to have to figure out the frequency of that light, and then once we have that frequency, we can figure out what the what actually kind of light is it, or what color it is, or that kind of thing. So when we look at these energy transitions as they move from our different levels, it creates different forms of light. So we often refer to that as the atomic spectra, or essentially what types of light are created from each individual atom. So this is the atomic spectra for the hydrogen atom. And you can see that anything that moves from a higher energy level back down to the ground state will create ultraviolet light. Anything from a higher energy level that goes to the n equals 2 state will create colored light, and then all the other ones create infrared light. As the gaps are larger, you get more high energy photons created. That's why as everything that goes from n equals 2 or anything higher down to the n equals 1 is ultraviolet, because you got a lot of energy in that transition. While the n equals 2 happens to be the sweet spot of where we get things in the visible spectrum. Now you can see the small jumps, like the n equals 3 to the n equals 2, makes a relatively low energy photon of red, if we're talking about in terms of color, versus the n equals 6 down to the n equals 2, we get violet. So, which is a higher energy thing. So the bigger the jump, the more energy that we get from it. Now you'll see some names given for some of these. These were basically when they were discovered. The person who discovered what these energy transitions are got them named after them. So the Balmer series is probably the one that we're going to be focusing on most, because those are the ones in the visible spectrum. Those are the ones that we can actually see when we're doing this. So speaking of seeing it, we've worked with the gas tubes before back in the light unit. I know we've seen them in chemistry before as well. When you excite those tubes of gas with the different colors with the different gases in them, they all create different colors. And that's what we're talking about here. What those tubes do is they cause electrons to move up to the excited state. Eventually, from the excited state, they go back down to the ground state. And when they do that, they release their photons. And the mix of colors that are released, in this case for hydrogen, we have the violet, green, and blue. When they're released, we then see them that make up when we're looking at the gases. So two classic examples of this, and the ones that we're going to be focusing on most in the Regents curriculum, is for hydrogen and for mercury. So each element has its own unique photons that it creates. They all have their own unique energy levels. And so as the photons drop, we're going to have many different types of photons released. And the ones that are in the visible spectrum are, of course, the ones that you can see. So when you excite hydrogen, you get these 4 distinct lines, which represent the Balmer series. You can see for mercury, we get many more different colors of lines. So we can actually identify the element based on what color of photons they are creating, which is pretty cool. So hydrogen, to be particular. So hydrogen has several in the visible spectrum, the 4 that we've talked about. So from the biggest energy drops, we have violet, we have our blue, we have our green, and we have our red. So if we have a continuous spectrum of color, you can see how they all kind of relate to that continual spectrum of color. And these are what we refer to as spectral lines, or the lines that we see when we actually do this. Now, if you guys remember from the gas tube lab that we did, they actually do form as distinct straight lines. And that's what we're looking at in that lab, and that's what we're talking about right now, are these energy drops and the lines that are created from them. And like I said, they're unique to each element, so we've been able to use them to determine things. This is huge for astronomy. We're able to determine what stars are made up of, what gases are in our galaxy and other galaxies. We're able to determine the makeup of these things because of these spectral lines, because of their unique fingerprints. As each gas creates their own color, we can determine, okay, what is that gas made out of? That's how we know that the sun is mostly made up of hydrogen. That's how we know, that's how most of the stars work, is because what we do is we look at the spectral lines to see what they're made up of and the percentages and all that stuff. It's very, very important for astronomy. All right, so here we have another example. Calculate the number of photons that create from the n equals 3 to the ground state. So this is a type of question that is not too uncommon. What I'm asking is how many different types of photons can be created, so different colors, when we move from the n equals 3 to the ground. The key thing to remember is when you're moving from a higher energy state to the ground state, doesn't mean you have to jump right there. So that is one of the possibilities. It can go straight from the n equals 3 to the ground state. That's definitely one possibility. But another one is that it can move from the n equals 3 to the n equals 2. So that's a second photon that's created. And then from the n equals 2 down to the n equals 1, that's a third photon that can be created. So how many in total can be created? Well, that's 3. Pretty simple, but you can see that once you get up to a higher energy level, like the n equals 4 or the n equals 5, then it starts to get more complicated as you have to deal with different jumps. So just get used to being able to count how many photons can be created for both hydrogen with this diagram and also mercury as well. As remember, they don't have to jump from the top all the way to the bottom. So one final topic is the ionization potential. Ionization is hopefully something you remember a bit from chemistry. It's essentially when we have the electron gains so much energy that it's no longer connected to its atom. It's essentially just left its atom. Ionization, of course, very important for bonding and things like that. But here we're focusing on how does light cause this ionization to happen. So if a photon of a very high amount of energy hits an electron, there's a chance that it can take that electron and knock it right off of its atom. That's what we refer to as ionization. The ionization potential is the amount of energy required to do that. And luckily for all of our diagrams that we gave you on the Regents reference tables, It's simply just the energy level that they're at. Here's what I mean by this. I'm just going to go back a couple of slides so I can get to this diagram. All right. So if an electron was in the n equals 1 state, then it would take 13.6 EVs of energy, electron volts of energy, to knock it off to eventually become ionized. If it was already resting in the n equals 2 state, it would take 3.4 electron volts worth of energy to knock off the electron. And that's what this n equals infinity stands for. That stands for ionization. So once there is 0 energy, that means that's enough to actually make it so it's no longer part of the atom. Now, the reason why these values are negative is because the electron likes to be with an atom. It takes less energy for them to be together than for them to be separated. So when they're separated, we call that our 0 point, and anything less than that, anything that's easier for the electron to be in, which is, of course, all these other states, with the ground state being the easiest, that's the one that the electron likes to be in most, we make negative values. All right, let's take a peek at some different examples that you guys can use when you're working on your worksheet, just so you can see how it's done. So we have a hydrogen atom going from the excited n equals 5 to the n equals 2 state. So what is the energy of the photon emitted? So the first thing you're going to have to do is open up your reference table and look at the hydrogen atom. I have mine open. Looks like the n equals 5 state corresponds to an energy of negative 0.54 electron volts. The n equals 2 state corresponds to an energy of negative 3.40 electron volts. So if we're trying to find our energy, we take the negative 0.54, subtract the, just erase that extra mark there, subtract the negative 3.4 electron volts from that. And when we do that math, we get 2.86 electron volts. So that is my energy of the photon emitted. Now, the next one is asking what type of electron radiation is created from this, and I gave that hint that is a multi-step question. So this will take a couple of equations for us to figure this out. The first thing we have to do is we have to switch our energy unit back to the SI system. And we talked about this in the last video. We have the 2.86 electron volts, and we're going to multiply it by the constant found on the front page of the reference table, and that is 1.6 times 10 to the minus 19 electron volts per joule. Oh, I'm sorry, joules per electron volts. And when we do that, we get 4.58 times 10 to the minus 19 joules. So once we have that amount of joules, then we need to figure out the frequency to determine what type of radiation it is. So we're going to use the Einstein formula we have. The E is equal to Planck's constant times the frequency. I'm going to plug in the energy I got here. I'm going to plug in Planck's constant that we get from the front of the reference table, which is our 6.63 times 10 to the minus 34 joule seconds. When I do that math out, I get a frequency of 6.9 times 10 to the 14 hertz. If you look that up on the reference table, you'll see that that is under the violet category. So that's how you do the first one. Now the second one is going to operate pretty much the same way in the front of the reference table, as the first part of the first problem, except the difference here is we're going to be looking at mercury rather than looking at hydrogen. And you can see if you're looking at mercury on the reference table, it has energy levels that are very different and less orderly than the hydrogen ones. So we're going from the, ground state to the G state. So we're going from an energy of minus 10.8 of the ground state, and we are ending up in the G state, which is 2.48 electron volts. So when you do this math out, you get 7.9 electron volts. And this is a negative 7.9, and all that stands for is that's the energy that's essentially going into the mercury atom versus being released from the mercury atom. So this 7.9 electron volts is the corresponding energy of the corresponding energy of the photon. So I asked you to find it in joules, though, in kilojoules to be exact. And so what we're going to do is we're just going to simply multiply that by that same constant, 1.6 times 10 to the minus 19. Actually, I don't know why I asked you for kilojoules. Let's just find it in joules. It's a mistype there. Let's just find it in joules. That's joules per electron volt. When you multiply those two values together, you get 1.264 times 10 to the minus 19 joules. That's pretty much it for that. Now, this final one is the example, very similar to the example that I did before. Now I'm asking you to figure out how many photons can be emitted from the n equals 4 to the n equals 1 state. I'm going to give you guys the answer to this. It's 6, but I want you guys to figure out what it is or how to do that on your own. So try to play around with it. I don't want to explaining all the answers to it. Just try to figure out how you can get 6 different photons going from the n equals 4 down to the n equals 1, remembering it has all those side jumps in between. So that's pretty much it for this video. If you have any questions, always feel free to email or drop something on the Google Classroom. Yeah, I hope this is going well for you guys. Have a good one.